Today, we're going to pull back the curtain on something that keeps our world from, well, blowing up. It's not some flashy new gadget or a team of superheroes. It's an invisible shield, a really meticulous set of rules, a checklist that makes sure incredible power stays under control. So yeah, let's dive in.
And you really have to ask, right? When you're dealing with these massive machines with insane pressures and stuff like ammonia, the line between everything running smoothly and a total catastrophe is incredibly thin. So what's standing in the way?
You know, the answer isn't some futuristic AI or one person's heroic moment. It's this, a checklist. Yeah, it might look kind of boring, but I promise you, this document is the unsung hero here. It's a carefully written script that spells out safety, step by step. Okay, so let's get into why this seemingly simple piece of paper is so unbelievably important. What makes a checklist the most critical tool in the box when you're working with machinery on this scale? Because every single line, every checkbox, is another layer of protection. Think about it. It's a way to take the guesswork out of a high-stakes job. It removes the chance for human error, especially when things get stressful. It's there to protect the lives of the people on the floor, for sure, but also the millions of dollars of equipment that keeps the whole operation running.
So that brings us to the very first part of the process, getting ready. Because real safety, it doesn't start when you flip the on switch. No way. It starts way before anyone even thinks about picking up a tool.
In this whole prep phase, it really boils down to three foundational ideas. First, you have to isolate all the energy sources using something called lockout/tagout, which physically stops the machine from turning on by accident. Second, you secure the area. Make sure you've got good ventilation, working detectors, the whole deal. And third, you confirm the system is stable, that you're not walking into a situation that's already on edge.
And right here, you can see what that actually looks like. The technician applies that lockout/tagout we talked about, literally putting a physical lock on the power source. They check that the ammonia detectors, basically an electronic nose for dangerous leaks, are up and running. They get into their personal protective equipment, their armor for the job. And this is so important, they make sure they have a clear line of communication with the control room. You're building a complete safety bubble before the real work even starts.
All right, so the technician is safe, the area is secure. What's next? Well, now it's time to test the machine's own built-in safety net. We're talking about the automatic systems that are designed to slam the brakes on if things start to go sideways.
First up is the high-pressure cutout. You can just think of this as the machine's emergency brake. If the pressure inside starts climbing too high, this thing kicks in and shuts the whole compressor down, stopping a seriously dangerous overpressurization event before it can happen. Now, here's where it gets really cool. The precision involved is just incredible. Look at that table. The technician isn't just checking if it works. They're making sure it trips within that super specific window, between 225 and 250 psig. That's pounds per square inch gauge. That number comes straight from the OEM, the original equipment manufacturer, the people who built it, and the test has to be perfect. Okay, next up is the oil differential pressure cutout, or ODP. This is basically the machine's life support system. Just like your car's engine needs oil pressure to keep from seizing up, this enormous compressor needs a constant flow of lubrication. If that pressure drops, this system shuts it down to prevent all those moving parts from grinding themselves into a pile of scrap metal.
And what's so smart about this one is that it's not just looking at one number. You can see it right there in the table. There's the pressure setting itself, a really tight window of 8 to 12 psid. But look at that other column, the time delay. The system is engineered to ignore a quick, normal little dip in pressure, but if the problem sticks around for more than 90 seconds, it shuts everything down. It's just a brilliant piece of preventative design.
The third safety system we're going to look at is all about temperature. Heat is the silent killer for these big machines. If they get too hot, metal parts can actually warp, and worse, the lubricating oil can break down and become totally useless. So this sensor is basically a fever detector for the compressor. And yep, you guessed it. Just like with pressure, the temperature has a very precise, non-negotiable limit. As you can see, the technician will actually simulate a high-temp situation to make absolutely sure the machine shuts itself down right in that 225 to 250 degree Fahrenheit window. No sooner, no later.
So, we've made sure all the automatic safety systems actually work. But how do those systems get their information in the first place? That, my friends, brings us to the calibration check.
This one line from the procedure says it all.
I mean, just let that sink in for a second. Adjust if deviation exceeds plus or minus 1%. The margin for error is almost zero. We are talking about an incredible standard of precision. And this really gets to the core of it. Any automated safety system is only as good as the data it's getting. The emergency brake is completely useless if the speedometer is broken, right? The cutouts we just tested depend entirely on their sensors. They're called transducers to tell them the truth about what's happening with pressure and temperature. So how do you make sure the machine's sensors are telling the truth? Well, you check them against a tool that you know is perfect. You compare the machine's sensor reading to a certified master gauge. It's kind of like setting your watch to the atomic clock. If the machine's sensor is off by more than that 1% we talked about, the technician fine-tunes it until it's perfectly in sync. Okay, deep breath. The safety systems are all tested, the sensors are perfectly calibrated. Now there's just one last crucial phase. We've got to bring this machine back to life safely and, close the loop on the whole procedure. And this is pretty much the reverse of how we started. All those locks come off the power sources, all the protective guards and panels get put back in place, they do a final check for any leaks, and then the paperwork. The checklist gets completed, filed, and most importantly, signed. And look, this is so much more than just bureaucracy. When that technician and their supervisor sign their names on that document, they're making a statement. They're personally guaranteeing that every single step was followed, that every safety system is good to go, and that this multi-ton machine is safe to run. It's a really powerful act of professional accountability. So in the end, that simple checklist is more than just a piece of paper. It's a shield, it's a script, and it's a promise. And it really makes you wonder, doesn't it? From the airplane you fly on to the electricity in your home, our entire world is running on a foundation of these invisible protocols for prevention, all of them quietly keeping us safe every single day.